welcome again. So today's lesson will be on the metals module of Year 11 Chemistry. And in today's lesson, we're going to look at Avogadro's law and how it relates to the mole. Okay, so we've been studying the mole quite in depth, and we're going to look at Avogadro's law. Like in the last lesson, we looked at Gay-Lussac's law. So what we're doing essentially is building up a history of how the mole was developed. Okay, and here, this handsome guy here is Avogadro, who's an Italian scientist, and he's contributed a lot to our understanding of chemistry. Okay, so Amadeo Avogadro is his name, and he was a famous Italian scientist that made a large contribution to chemistry. Okay, so he was the guy that the mole is essentially characterized by. In particular, his contributions surrounded the concept of the mole and led to advances in molecular theory. Okay, so obviously you know Avogadro's number and how it relates to the mole, and obviously it's named after him. And he led great advances in molecular theory as well as the mole. Okay, so that's what we're getting at. Okay, so Avogadro's law. In 1811, Avogadro proposed that some elements may exist as atomic aggregates, which he called molecules. So that doesn't mean much to you, right? But atomic aggregates, all that means is that while Dalton said that all elements exist as singular atoms, and if I keep chopping up a block of gold, I chop it into a half, and then I chop it into another half, and I keep chopping it trillions upon trillions of times, I'll eventually get to a stage where if I chop it in half, I'll get to something that I can no longer break down. I'll get to a single gold atom, right? And that was the theory at the time, Dalton's atomic theory, that everything exists as singular atoms of a particular element. And those elements can bond together to form new substances. But if I was to look at an element, the smallest unit of that element would just be one atom. But if you're thinking about oxygen, you've got this thing. Oxygen gas, the element, exists as O2. So obviously Dalton's atomic theory doesn't fit this model because we know oxygen exists as O2. And Avogadro was the first person to sort of identify this. He realized that some elements actually exist as what he called atomic aggregates, which means that there's atoms linked together, clumped together, like this. And he called those clumps molecules. Okay? And we call them molecules now as well. Okay? So that's what we mean by atomic aggregate. They're just clumps of atoms of the same element bonded together that form the basis of that element. That is the smallest unit of that element that can naturally exist. Okay, and we call them molecules. Okay, so here we have, hydrogen plus oxygen giving us water, and they're existing as diatomic gases. Okay. So what is Avogadro's law? Well, Avogadro's law says that at constant temperature and pressure, so you have to make sure the temperature and pressure are the same, otherwise this doesn't hold. Equal volumes of any gas contain equal numbers of molecules. Okay, so if I have 1 liter of a 1 liter container filled with gas at pressure P and temperature T, then whatever that gas is will have the same number of molecules as if I took out that gas and put in methane, or hydrogen, helium, neon, oxygen, any of these gases. As long as the pressure is P and the temperature is T, the number of molecules in that volume will be exactly the same. Okay? And that's a very big statement, and that tells us a lot. Okay? So Avogadro's law and the mole. So here we have Avogadro's number. It's a massive number, as you can see. So Avogadro's law relates the volume of gas to the number of particles within that gas. Okay? This links the volume of an ideal gas to the number of moles of that gas. Okay? So these two statements look really similar. But what they mean is, this one says that the volume of a gas in space tells you how many particles are in that gas. Okay? Whereas this statement says that the volume of a gas will tell you how many moles are in that gas. And essentially they are the same statement. They're just very subtly different that I decided to put them both in because it'll help you understand what's going on. So if you know the number of molecules, you instantly know the number of moles because you can use this guy, 6.023 times 10 to the 23, to work out the number of moles, or vice versa. Okay, so these two statements are quite interchangeable. Okay. And Avogadro's law allowed scientists to essentially measure the molecular mass of several different gases. So Avogadro's law helped us to figure out what the molecular mass of a particular substance is. Okay. So then moving on to moles and chemical equations. So this is sort of where we're going. We looked at the history of moles. Now we're going to look at more practical aspects of it. So the stoichiometric coefficients in a chemical equation describe the ratio of moles required in that reaction. So ratio is the word here that we're going to talk about. So it's the ratio of moles, not the ratio of molecules. Now there's a very subtle difference in that word, and the difference is that you can have half a mole, but you can't have half a molecule. And so that's a very subtly different point. Now because they relate to moles and not molecules, it's why that we can have stoichiometric coefficients that are non-integer numbers. Okay? I don't mind having equations that have 3.5 O2 in them. I have no problem with that. Many chemistry people do. They don't like it. It looks sort of messy, and lots of people like things to look pretty. But I personally have nothing against that. And in general, there's nothing wrong with using non-integer coefficients because they only relate to the number of moles. And the number of moles is very different to the number of molecules. So for instance, if we have this equation, you can see you've got 2 HCl, 2 moles of HCl for every 1 mole of magnesium. So in this reaction, for every 1 mole of magnesium, 2 moles of hydrochloric acid are required. Okay? So if we had, for instance, something like this, whatever on this side, this is okay. 3.5 is fine because it's the number of moles, not the number of molecules. If I wanted the number of molecules from this, I could multiply by 6.023 times 10 to the 23, and I'll still get an integer number because 6.023 times 10 to the 23 will give me a very huge number, even if there is a half in there. So I'll still get an integer number of molecules, but I don't need an integer number of moles. Okay? Just something to be aware of. And also, if you do future studies in chemistry, you may see more and more that non-integer numbers come up fairly frequently. So that concludes our lesson on Avogadro's law and the mole concept. So we looked at Avogadro's law, and we looked at how we utilize that and how it relates to the mole. Okay, and we also looked at how the mole relates to the different coefficients in a chemical equation. So I'm going to move on to the question segment now, and hopefully you'll learn something more, or at least reinforce the things that we learned in today's lesson. Question 6. Outline how Avogadro's law has allowed scientists to compare the molecular masses of different gases. Well, Avogadro's law allows us to determine the number of particles within a set volume. So assuming the pressure and temperature are kept constant. So if we keep the pressure and temperature constant, then we can work out the number of particles. By defining a constant volume, so by saying the volume is this, that's what I mean by defining. We just say whatever volume we want. Probably easiest to say a meter cubed, just for the mathematics, but anyway, it doesn't matter. And ensuring that the pressure and temperature are the same, the molecular masses can be determined. So by weighing the volume of gas and knowing from Avogadro's law the number of particles within the volume, the mass per particle can be known. Okay, so if I have a container, here's my container, and I put particles inside it. Okay, I weigh the container. It has mass m. Okay, so the mass of an individual particle would just be m divided by the number of particles, right? And then that's how we can work out the mass of a single particle of a particular chemical, or the molecular mass of that particle. Okay, and that's all using Avogadro's law, and that's where we get how we know that. Okay. Question 7. 5 moles of ethanol, which is this C2H5OH, is reacted with O2 to produce CO2 and H2O. So we write a balanced chemical equation for this reaction. So the general or pseudo equation is just this, A, B, and C. We know that CO2 and H2O are our products. We know that this is our reactant and it has to react with oxygen. So we will balance this chemical equation. So we balance for carbon. There's 2 carbons on the left and B carbons on the right. So B has to be 2. Then we balance for hydrogen. There's 2 C carbons on the right and 6 hydrogens on the right and 6 hydrogens on the left. So 2C has to equal 6. So C equals 3. And then balancing for oxygen, 1 oxygen plus 2A equals 2B plus C oxygens on the right. Okay. So 2 times 2 is 4 plus 3 equals 1 plus 2A. Then if we do the maths, 2A equals 6, so A equals 3. So the final reaction or chemical equation is 1 ethanol molecule, or 1 mole of ethanol plus 3 moles of oxygen gives you 2 moles of carbon dioxide and 3 moles of water. Okay. And we're just going to keep it in here just because we want to use it later. So determine the number of moles of oxygen required for this reaction. Well, for every 1 mole of C2H5OH, 3 moles of oxygen are required from the equation. Therefore, for 5 moles of C2H5OH, 15 moles of O2 gas are required. Okay? So remember, we start with 5 moles. So if there are 5 moles, we need 3 times as many, so it's 15, and that's the end of the question. Okay? So magnesium strip is dissolved in sulfuric acid. The resulting reaction produces 2.05 liters of hydrogen gas. Calculate the mass of magnesium used in this reaction if 1 mole of an ideal gas takes up 24.79 liters. Okay? So we start with our chemical equation. Mg plus H2SO4 gives us hydrogen gas and magnesium sulfate. So first we calculate the number of moles of H2, which is the volume of the H2 divided by the molar volume of an ideal gas. So it's 2.05 times 24.79, divided by 24.79, which is 0.0827 moles. And then from the equation, we see that NH2 equals NMg, so it's 1 to 1. So the number of moles of H2 equals the number of moles of magnesium, which is 0.0827. Then finally, the mass of the magnesium equals the number of moles of magnesium times the molar mass of magnesium. And so the molar mass of magnesium, we look on our periodic table, multiply by the number of moles, and we get 2.01 grams. So 2.01 grams went in to produce 2.05 liters of gas out. Okay. Question 9. Coal, carbon, is burned in oxygen to produce CO2. If 1 ton of coal is burned, what volume of CO2 gas is released if 1 mole of ideal gas takes up 24.79 liters? Okay. Well, here's our equation. C plus O2 gives you CO2. Very, very simple. So N of the carbon equals the mass of the carbon over the molar mass. So 1 ton is 1,000 kilograms, and 1,000 kilograms is 1,000 times 1,000 grams. So that's why we have all these thousands up here. And the molar mass is 12.01. So this is just converting units at the top. So we have 83,263.95 moles of carbon used. And from the equation, for every 1 mole of C consumed, 1 mole of CO2 is produced. So number of moles of C equals the number of moles of CO2. So the number of moles of CO2 is 83,263.95 moles. So the volume is just that, this number, times the molar volume there. So there's our answer. And so it's that's 2,064,113 litres. Okay? And if you want to change that, it could be 2,064.11 meters cubed, or 2.064 kilometers cubed. Okay? So that's the answer. Okay? Question 10. 10 grams of magnesium is reacted with 15 grams of oxygen to produce magnesium oxide. Which of the two reactants is in excess? Okay. So there's our equation. Magnesium plus half oxygen gives you magnesium oxide. We want to know the mass of the magnesium. So there's number of moles is 10 over 24.31, which you look up on your periodic table, which is 0.411 moles. Number of moles of oxygen is the same, just with different numbers, 15 over 32. So 0.46875 moles. And from the chemical equation, the required amount of O2 is half the number of moles of magnesium. So in this case, the required amount of oxygen is 0.2055 moles. Therefore, since there is more O2 moles present than required, the O2 is in excess. Okay? Make sense? So that concludes today's lesson on Avogadro's law and the mole. We looked at Avogadro's law, we looked at how the mole relates to stoichiometry, and we did some questions calculating different aspects of the mole using volume, mass, and chemical equations. So in the next lesson, we're going to look at the ideal gas law and see how the ideal gas law brings it all together in a nice little theory in itself. So I look forward to seeing you in our next lesson.